Okay, so in the last couple of clips, we learned that the scalars are quantities that have only magnitude, how much of something, and we know that this would be speed, distance, and time. And we learned that vectors are quantities that have magnitude and direction. And we know that this would include velocity, displacement, and acceleration. We know that um, displacement is the change in position, x final minus x initial, x minus x naught. We know that the average velocity is defined as the displacement over time. We know that acceleration is change in velocity over time. And now this is actually an average acceleration, but if you will recall, for us, accelerations are constant, so we don't need to really worry about that at this time. And we remember from the definition of acceleration, we got our first equation of motion. V is V naught plus AT. Um, and this is where we left off. Now, a little bit that I want to add to the acceleration. It is important to remember that velocity and acceleration are both vectors. So if we have linear motion, and let's just imagine an object that's moving back and forth on some number line, perhaps. Um, so we would have a negative direction and a positive direction. And so we could actually express velocity as so many meters per second, positive or negative, and that would include our directions. But if you are like me, before you learned physics, you always thought that acceleration meant speeding up. And in physics, that's not necessarily the case. If you look at it, any change in velocity uh, will result in an acceleration. So that means it could speed up, it could slow down, and perhaps it could even change direction. All of those would count as accelerations. But if velocity is a vector and we have an object that is moving in the positive direction, and it has acceleration that is also in the positive direction, then that object would be speeding up. However, if it had negative acceleration, then the object would be slowing down. So using this coordinate system, if the acceleration and the velocity are both to the right, then this object is moving in the positive direction. But speeding up. And if the object had velocity in the positive direction and acceleration in the negative direction, then this would be moving in the positive direction, but slowing down. Okay, we could move to the left if we had velocity to the left and acceleration to the left. This would be moving in the negative direction and speeding up. Or perhaps moving in the negative direction with positive acceleration In this case, that would be moving in the negative direction and slowing down. So it's important to pay attention to the direction of vectors. We don't say slowing down or speeding up, we say accelerating. And the acceleration can be positive or negative. If an object is speeding up, the acceleration will be positive or negative along with the velocity. If it's slowing down, the acceleration will be the opposite sign of the velocity. So please keep that in mind. Looking at a little bit different situation now. So let's imagine that we have a vehicle, and this vehicle is moving to the right with constant velocity. So it's not speeding up, it's not slowing down or changing direction, it's moving in a straight line with constant velocity. And we evaluate the motion of this car as it passes a point we've designated our initial position, x naught, and 100 meters to the right it passes our final position, x, and this time was 5 seconds. So if we were to graph the position of this car moving at constant velocity over the time, we would get a linear graph. And the reason for this is because at a constant velocity, the vehicle in any period of time is going to move the same displacement. So every second it will move the same displacement. In the next second, since it has the same velocity, it will have the same displacement. In the third second, it will have the same displacement, and so on. If we were to gather the position at each second and plot that versus the time, we get this linear graph. And now what we can learn from this linear graph is relatively interesting. For example, if we wanted to know, and let's pay attention to the fact that this is a displacement time graph. That's too tedious. I'll just call it a DT graph from here on out. So on a DT graph, the slope gives us something interesting. So slope, we know, is the rise over the run, the change in the y value over the change in the x value. So for any segment of this line, this change in y value is actually the change in x. Look at the axis, the change in x. And our horizontal value is our change in time. So the slope of a dt graph is delta x over delta t. If I'm not mistaken, that's what we call average velocity. So it is worth knowing on a DT graph that the average velocity is the slope of the line.